Fundamental Manufacturing Processes video series, examining the tools and techniques of precision metalworking. This program is an introduction to work holding for milling and turning. Work holding is a fundamental issue in performing any machining process. Work holding includes any device used to grip and present a workpiece to a cutting tool on a machine tool. It includes clamps, vices, fixtures, chucks, and more. The decision on how to hold a part influences which surfaces or holes are designated as reference surfaces or datums, which surfaces can be machined in a setup, the accuracy of the machining process, the allowable cutting forces, and thus possibly the cutting feeds and speeds, and the tool path and possibly tool size and shape. Work-holding devices must also suit production demands. They should be easy to unload and load. They must permit access of cutting tools to the workpiece so that multiple operations may be performed in one clamping. The work-holding setup and teardown should be as simple and as fast as possible. And for economy, standard catalog items must be used where possible. A machined part has certain planes, lines, and/or holes from which other points are measured. These reference points or planes are called datums. To correctly machine a part, it must be held in a setup that guarantees a definite location or position and orientation in space with respect to the part's datum points or surfaces. This must be repeatable part after part. Secondly, the work-holding device must hold the part securely in position while cutting forces, vibrations, centrifugal force, and gravity act to dislodge it. In theory, the location and clamping of workpieces are considered separate issues, but in work-holding practice, locating and clamping are integrated as part of the same process. The holding action ensures the workpiece is stable for machining once located. If not restrained adequately, the workpiece will move and become scrap. Conversely, the clamping force must not be inappropriately excessive, so as to distort, gouge, or break the workpiece. Work holding starts from visualizing the coordinate system representing a solid object in space, known as the 12 degrees of freedom. These 12 coordinates consist of the plus and minus movement in the x, y, and z axes, and the clockwise and counterclockwise rotation around each of these three axes. These 12 directions are the ways in which a workpiece may move. Once a workpiece is properly located in space and secured, all 12 degrees of freedom are canceled. Locating may be done from circular, irregular, or plane surfaces. The 3-2-1 locational method is suited for rectangular parts located by their outer edges. With this method, 6 points of contact, or locators, on the faces of an object cancel 9 of the 12 degrees of freedom. These 6 contact points include 3 primary locators, 2 secondary locators, and a single tertiary locator. The 3 primary locators establish the plane upon which the part rests. These locators restrain 5 of the 12 degrees of freedom, the down direction, or minus z axis, and the 4 rotary motions around the x and y axes. The 2 secondary locators are 90 degrees to the primaries and in the established plane. These locators restrict 3 additional degrees of freedom, the plus y axis and the 2 rotary motions around the z-axis. The final tertiary locator is found 90 degrees to the secondary locators. It restricts the minus x-axis. Together, these 6 locators absorb the primary machining forces. When a clamping device is added, the 3 axes which remain, the plus x and z, and the minus y axes are secured for machining. For accuracy and productivity, as many operations as possible should be completed in a single clamping. Reclamping or rechucking have 2 negative impacts. First, When the workpiece is moved, the location of the workpiece in relation to the machine tool is lost. That compromises the accuracy of the part. Secondly, setup time doesn't add value to the workpiece, and machining time is wasted at each unclamp-clamp cycle. Although a single clamping is ideal, 2 or more clampings or chuckings may be required when datum surfaces must be machined first, or a through hole has steps on both sides, or a part has blind holes on opposite sides. Work holding for milling should be matched to the production level. For small lot production on milling machines, the simplest clamps or vices are used. For medium lot production on machining centers, quick-acting single and multiple clamping devices are used. If volume warrants it, hydraulically operated clamps can be utilized. For mass production of a part, a dedicated fixture can be built. Manually operated clamps are the simplest work-holding device for milling. Clamping must be strong since the cutting forces change directions as the milling cutter enters and exits the part. Clamps must also act quickly for fast loading and unloading and not damage the workpiece. There are many basic clamp types. Some are the strap clamp and the cam clamp. Toggle action clamps have an excellent ratio of holding force to application force. They work quickly and have a positive locking action. The most popular toggle clamp is the hold-down design, which holds the part with a downward clamping action. Other types of toggle clamps include the push-pull clamp and the latch clamp. Vices hold a great many shapes. They clamp manually or automatically. One variation has a fixed central jaw and 2 moving jaws to hold 2 or more parts in less space than 2 separate vices. Swivel or tilting bases allow the vise and work to be set at an accurate angular position relative to the machine axes. Pairs of vices extend the range of what may be held, such as long parts. To minimize setup time on machining centers, vices may be arranged around a cube or column or on an indexer or rotary table. Parts may also be held on 2, 3, or 4 sides of a tombstone or indexer, with identical or different workpieces clamped on different sides. Multiple small workpieces may be clamped in position and machined one after the other. A rotary table allows 4 sides of a workpiece to be machined in one setup and allows the machining of holes and surfaces at odd angles. Rotary tables are of 2 types. There are indexing tables, which quickly index to a fixed position of angular rotation and lock in that position for machining, and full rotary tables, which traverse during cutting to generate shapes. On some horizontal machining centers, rotary work tables are built in. But sometimes, a second accessory rotary table is placed atop the first to add another axis. Modular fixturing systems allow you to build fixtures quickly from a kit of various components. This maximizes flexibility and cuts assembly time. Standard interchangeable fixturing components include base plates, supports, locators, and clamps. Modular systems start from a pattern of locating dowel holes and tapped holes, or from conventional T-slots. A T-slot-based system starts from T-slotted base plates. Fixture elements, like clamps, are attached to the base plate, angle plate, and so on, to create the fixture. Clamping is usually manual, but may be power-assisted. Like T-slotted machine tables, the T-slot system has one major disadvantage. It lacks exact fixed references in the X and Y axes. Time is wasted when locating and reconstructing previous setups. Precision dowel pin-based modular fixturing systems do assure the exact position of each fixture element. Its disadvantage is that the dowel pin layout may restrict the location of the clamping devices. Many horizontal machining centers accept workpieces clamped to pallets and change pallets automatically in seconds. Fixturing is built on the pallets rather than on the machine table. Workpieces are unloaded and loaded on the pallet outside the machining zone. Pallets in a horizontal machining center may be swapped in and out on parallel tracks, or with a rotary table that allows one pallet of parts to be machined while another is outside in the setup zone, or with an automated machining system or cell in which a rail-guided cart swaps pallets from pallet storage racks to the machining center's setup zone. For vertical machining centers without pallet automation, many users add a manual pallet switching device or a wheeled table holding pre-fixtured workpieces. One approach with small workpieces is to store mini pre-fixtured pallets for those parts run repeatedly. Keeping the work holding in storage minimizes setup times. If the mini pallet mates with a fixed pallet receiver of known location on the machine table, then there's no need to locate parts within the machine tool's workspace. Hydraulic clamping is common in higher volume applications, where the speed gained is worth the investment. Hydraulically operated clamps work for thousands of clamping cycles, and many can be combined around a workpiece. When the operator pushes the button, multiple clamps move simultaneously to grasp and hold parts on a fixture. Application-dedicated fixtures are used primarily for mass production. Fixtures are designed concurrently with the special machine tools for highly accurate part location, foolproof part loading, and simple automation. Dedicated fixtures are the opposite of modular fixturing. There is no flexibility. Instead, dedicated fixtures offer speed, reliability, and accuracy over the product lifetime. Chucks are utilized in milling to locate and clamp stationary, round workpieces to machine tables. Location is not affected by variation in workpiece diameter. Pallets and tombstones may also be equipped with multiple chucks to hold round parts in a machining center. In turning, the workpiece rotates instead of the cutting tool, so the work-holding requirements differ. The work-holding devices must transmit torque to rotate the workpiece and withstand the centrifugal force developed by that rotation. Lathe work-holding devices include the chuck, the collet, the mandrel, and a means of rotating the work for between-center turning, such as a drive dog or a face driver. The self-centering three-jaw chuck, either manual or power-operated, is the most common and economical form of lathe work-holding. Self-centering chucks may also be six-jaw. In 3- and 6-jaw chucks, a stop sets the length of the work, while the jaws establish the concentricity of the workpiece with the lathe spindle. The 3 moving master jaws have serrated teeth and are mounted 120 degrees apart within the chuck body. They move simultaneously. Atop the master jaws sit interchangeable top jaws. The teeth on the bottom of the top jaws engage with the teeth of the master jaws. Top jaws clamp the workpiece or bar stock for turning. Standard top jaws are made in sets of 3 and are of a variety of designs for different applications. Top jaws clamp inward to grab outside diameters and outward to grab inside diameters. Where accurate concentricity with a previously machined diameter is required, soft top jaws may be made. These are bored to size after they are mounted in position on the master jaws. 3-jaw chucks designed for CNC lathes are automatic, activated by a foot switch or other switch to open and close. Hydraulic-type chucks require a draw tube, or in smaller chucks, a draw bar to activate the chuck. By adding a support, such as a tailstock center, to the end of the workpiece opposite the chuck, the length of work extending from the chuck may be increased several times. The 4-jaw chuck is used for non-symmetrical or non-round work that must rotate on a center line. Work centering takes time, as each jaw is adjusted independently. Some non-round workpieces fit better in a 2-jaw chuck, in which the jaws are specially machined to grip that piece. Setups in both 4-jaw and 2-jaw chucks must be tested for balance before being rotated at turning speeds. Workpieces that have intersecting axes, such as valve bodies, may be machined on 2, 3, or 4 surfaces in an indexing chuck. These chucks index the workpiece, presenting several sides to the cutting tool. Jaws for indexing chucks must be custom-made for the workpiece. Collets clamp accurately on smooth surfaces without marking or distorting the part. Collets come in a wide range of sizes and types and are typically used to support round bars or cylindrical slugs. Standard collets are also available in square and hex shapes. Some collets are multi-sized, with a stepless gripping size range of about 1/8 of